This is the Math 217 lecture on the sampling distribution of a proportion. This is the beginning of a major transition. We're going to take what we learned about probability and in particular random variables and apply it to what we did early in the semester, which was all about variables, populations, samples, and ultimately we will use this to infer information about the population from knowledge of the sample. But we will start less ambitious than this. Let's just start thinking about a variable. In fact, let's think about a population and a binary variable. So the population, let's say, is adult Americans, and the binary variable is whether or not you believe in God. So remember, there's really one significant parameter to consider there, which is the population proportion, p. Remember, parameters are usually supposed to be Greek letters, but this violates that rule. It's the letter p. In this case, let's suppose that 82% of Americans believe in God. This is a reasonable number, but as you can probably guess, the percentage you get depends heavily on exactly how you ask the question. Now I want you to imagine taking a sample, let's say a sample of 400 Americans, and ask them if they believe in God. How many are going to answer yes? Well, you would expect it to be close to 82%, but not exactly, right? So the key statistic that we would be interested in is the sample proportion, and that's generally called p hat, p with a little caret over top of it. That's the number of yes answers divided by the total, which in this case is 400. It's the proportion in the sample who believe in God. And here's a simple but fundamental point. Each sample has a different p hat. As you run through all the possible, if you imagine all the possible samples you could take of size 400 of adult Americans and wrote down the p hat for each one, you'd have a huge list of numbers. My question is, if you made a histogram from those numbers, what would it look like? So here I'm viewing a random process as picking a simple random sample of 400 people and computing the sample proportion p hat. That is a repeatable process, uncertain outcome, and the outcome's a number. It's a random variable. We'll call that random variable capital p hat, because random variables have capital letters. Of course, this means that absolutely everything that we talk about has a variation of p as its name, which is unfortunate. The basic point of this lecture is there are 3 facts under good conditions that you know about the sampling distribution of p hat. 1, its mean is p. 2, its standard deviation, in this case we're going to call it standard error, is square root of p times 1 minus p over n. So I label those mu sub capital p hat and sigma sub capital p hat to remind you what random variable they're the mean and standard deviation of. And finally, it's a normal distribution, if n is big enough. I want to stop and point out that the first of these statements is completely reasonable, and you might have predicted, because what it's saying is sometimes p hat will be bigger than 82%, sometimes it'll be less than 82%, but on average it's going to be 82%. So that's all this is saying, and it's, fits your intuition. I'm not going to claim that that formula for the standard deviation fits your intuition. But I will say this, it only depends on p and n, and notice you're dividing by n. So the bigger n gets, the smaller the standard deviation gets. And that should fit your intuition, because what's that saying? That's saying if you have a big sample, you're probably going to get a number pretty close to 82%. There's going to be little variation. If you have a sample of 5 or 10, you could be anywhere from 0% to 100% believing in God. So qualitatively, the formula is plausible. Now, those 3 statements are only true if certain assumptions are met. And I'm going to spend some time talking about those assumptions. The process, everything we do from here on in will rely on assumptions. And it will always work the same way. This is universal to statistics. There's the actual formal assumptions, which are theoretical statements which are almost never true in practice. But then there is the good enough. We will write down rules of thumb, which are, in this case, it's close enough to the theoretical assumption that the calculations still work well enough. Okay? And we will learn to apply the rules of thumb. When you go out in the real world, there's a lot of judgment involved. The rules of thumb become fuzzier, but in here they'll be pretty precise. Roughly speaking, there are three assumptions, and the first one you need to get any of those three statements. The second one you need to get the last two. The third one you need to get the last one. So they're paired with the statements. We will sort of pay attention to that during this lecture, and then pretty much forget about it and treat the checking of the assumptions as this sort of separate thing from the doing of the calculations. That's just sort of a practical thing in terms of making the flow easier, even though logically it doesn't make as much sense. The first assumption is that your sample is a simple random sample. Of course, everything we do assumes that. As you know, this is rarely true in practice, and usually it's considered good enough if your non-randomness, if you cannot identify any plausible sources of bias in your non-randomness. So if it's a simple random sample, then that statement about the mean being p is true. Standard deviation, you need a little bit more. You're literally assuming that each person you sample from the population is independent of the others. What does that mean? Think about when we drew cards from a deck. If you draw cards from a deck, put them back in and shuffle each time. You draw a sequence of cards. Then what happened the first time has no effect on what happened the second time. They're independent. Life got more complicated. Remember the example when we drew two cards. If the first card was an ace and we don't put it back, there are now fewer aces. The probability of an ace goes down. Drawing cards is just like picking people for a sample. If I pick somebody who doesn't believe in God first for my sample, then the number of people in the population who don't believe in God has gone down. That makes the calculation of the probabilities more complicated. So to make them simpler, we generally assume that we're sampling with replacement. Just like you put the card back in and shuffle, you imagine throwing the person that you just asked the question of back in. Literally, that would mean you're prepared to pick their name out of the hat again and ask them the same question twice, which of course you would not do, and it doesn't really make sense. However, I think it's clear that if your population is large, if there's thousands of people who don't believe in God, when you pull one out, you haven't really changed the proportion significantly. So if it's a large population, successive individuals chosen from it are effectively independent. How large does it have to be? Our rule of thumb is the population should be at least 20 times the size of the sample. Be careful with this one because it kind of runs opposite to your intuition. You would think you'd want the sample to be a large fraction of the population. This assumption says it can't be too big a fraction. So be careful that you don't reverse it when you check it. On the other hand, you don't need to worry about this assumption very much because it's almost always true. When it's not true, there's a fairly easy fix, which we'll talk about at some point. Finally, the basic fact is that as n gets bigger, as your sample size gets bigger, the distribution of p-hats gets closer and closer to normal. It does so faster if p is sort of middling. If p is around 0.5, it happens pretty quickly. If p is very close to 1 or to 0, it takes longer. It tends to be kind of skewed. So to combine those cases in a simple way, we use the rule of 15. So the normality assumption, you can assume your distribution is normal if the numbers n times p and n times 1 minus p are both at least 15. So let's see what this looks like in practice. Remember, 82% of adult Americans believe in God. Suppose we take a simple random sample of 400 adult Americans and ask them if they believe in God. What are the mean and standard deviation of the proportion in your sample who believe in God? We'll also find what's the chance that 80% believe in God, and what's the chance, less than 80% believe in God, and also what's the chance that between 80 and 90% believe in God. So I'm going to go through and check each assumption before I draw my conclusions. Again, We'll do that this time to get you the feel of the logic. In the future, we will just check the assumptions separately from doing the calculations, just because it makes the flow and straightening things out easier. First assumption, simple random sample, it says, and in general, checking that assumption is totally straightforward. Either it says, or it doesn't say, or sometimes it describes a situation, a sampling method, well enough that you can tell it's not a simple random sample. But if it doesn't say, it's not met. So we're justified in assuming that the mean of p hat is p, which in our case is 0.82. On average, your sample proportion will be 82%. Next, let's check the large population assumption B. We need the population to be more than 20 times the sample size. The sample size is 400, so we need the population to be at least 8,000. Of course, there are way more than 8,000 adult Americans, so that assumption is met. That means we can compute the standard deviation, which is the square root of p, which is 0.82, times 1 minus p, which is 0.18, divided by n, which is 400. In Excel, you would say equals SQRT, open parentheses, 0.82 times 0.18 divided by 400, close parentheses. Careful with your parentheses, and in particular, you may find it easier to do the subtraction in your head. 1 minus p I just did in my head as 0.18. That might actually be easier than putting 1 minus 0.82 in parentheses and possibly messing up the parentheses. Your call. But here we end up with 0.019, about 2%, and that's a pretty typical standard deviation of the sampling distribution. We call it a standard error. For this size sample, bigger samples it may get a little less, smaller samples it might be a little more. And finally, we need to check the normality assumption, which is the rule of 15. We compute n times p, 400 times 0.82, that's 328, of course that's more than 15, and we compute n times 1 minus p, 400 times 0.18, 72, that's more than 50. Since both are met, we can assume p hat is normal. Okay, and here's the payoff. If you know a variable is normal, you know its mean, and you know its standard deviation, you know everything about it. So when I ask, what's the chance that less than 80% in your sample believe in God, you use norm dist, right? The probability that p hat is less than 0.8, because p hat is normal, is norm dist. 0.8 goes first, the mean goes second. Here's our standard deviation, comma, our ritualistic one, close parentheses, and that works out to 14.9%. I want to throw in one word of caution. I put this whole formula in instead of 0.0192 for the following reason. This calculation tends to be very sensitive to the standard deviation, meaning if you round it off too much, if instead of 0.0192 I had said, oh, that's 2%, 0.02, I would significantly, or sometimes I can significantly change the probability, sometimes by a factor of 10. In particular, if you do that and don't write down carefully for me what you did, I may see a number that I will never guess was gotten by the correct calculation with a little bit of rounding. So you run the serious risk of getting a significantly wrong answer, and you run a potential risk of my not realizing that it was a small mistake and thinking it was a huge mistake. One way to solve this is to just make sure you round off to enough decimal places. That depends on the mean and the variables, the value you're comparing it to, but a simpler or a more foolproof way to do this is not round at all and put the exact formula in there. So let me quickly show you this calculation. So I'm going to say equals norm dist 0.8, the mean was 0.82, and now I'm going to write out the formula for the standard deviation. Square root is the function. You can see it prompts me and knows the square root. And then p times 1 minus p was 0.18 divided by n, which is 400. I close off the square root parentheses, put my ritualistic 1, close off that parentheses, and there's my 14.9%. Okay, likewise, if I want the probability between 80 and 90%, which is p hats between 0.8 and 0.9, I do norm dist of the bigger, 0.9, minus norm dist of the smaller, 0.8. Everything else stays the same, and that's 85.1%. Notice, a mean of 0.82, a standard deviation of 0.02, so 82 and 2% if you prefer. Between 80 and 90 is from 1 standard deviation below the mean to 4 standard deviations above the mean. So you would guess it is all but about a sixth, which is about 85%. That's a reasonable number. Okay, that is the basic thing we've learned. We're learning how to do this lecture. Find mean, standard deviation, and check those 3 assumptions, and use the mean and standard deviation and the normality to compute probabilities. I'm going to step back and look at the big picture of this because it's a paradigm for a lot of what we're going to do in the future. What we saw is that if you take many samples of n equals 400 from a population where the proportion of successes p is 0.82, and you compute the sample proportion p hat for each one, these values will have a normal distribution with a mean of 0.82 and a standard deviation of 0.019. In other words, you can predict what will happen when you take a sample as a random variable in any way that you like. Anything you want to know, norm dist, or maybe norm inv will tell you. So those 3 things, normal distribution, the mean, and the standard deviation, are what we can predict. In general, we are going to look at a lot of situations where we have a population and a variable. We take a simple random sample and we compute some statistic, the mean, the proportion, the slope of the least squares line, all sorts of things. Each time you pick a random sample and compute a statistic, you get a different answer. Since the answer is a number, that's a random variable. We're going to talk about this all the time. That random variable, its distribution, is always called a sampling distribution. Okay? And when we talk about the standard deviation of a sampling distribution, we remind ourselves that it's this funny distribution by calling it standard error instead of standard deviation. That's just what people do. And in general, we're going to be interested in its mean, its standard deviation, and its shape. I want to give you a caution and teach you some terminology that the book is very fond of. The caution will take time to process, but what's confusing about this stuff is we're dealing on 3 levels. One level, which is kind of abstract, is the population. The population distribution refers to all the values of the variable in the population. So in our case, you describe the population distribution when you say that 82% of all adult Americans believe in God. The second level, and now in our case, we know that. Usually we won't know what P is. We'll just be picturing this population distribution. It will be abstract. We'll be hoping to infer things about it. The data distribution will typically be very concrete. You will take a sample and you will write down, in your sample of 400 people, you will write down 320 yes answers and 80 no answers. That's your data distribution. That is the information from your sample. The third level, and most abstract, is the sampling distribution. That is, imagining taking all possible samples, computing the statistic in each of them, and looking at that distribution, asking about its mean, its standard deviation, and its shape. And it's that which will allow us to connect the data distribution to the population distribution. We will use the sampling distribution to infer information about the population distribution from the data distribution. Okay, so after watching this lecture, here's what you should be able to do. You should know what we mean by the sampling distribution of p hat and what it represents. It represents all possible values of p hat for each sample you could imagine taking from your population. You should be able to calculate the mean and standard deviation of p hat. Mean is p, standard deviation is square root of p, 1 minus p over n. You should be able to check all three assumptions. Simple random sample is straightforward. You should be able to check the large population assumption, that the population is at least 20 times the sample size, and know that means that the standard deviation formula is then legitimate. You should be able to check the normality rule of 15 assumption, that n times p and n times 1 minus p are both at least 15, which tells you that it's a normal distribution. And finally, you should be able to calculate probabilities of p hat using norm dist.